The 20th century witnessed a technological revolution that reshaped the entire world. Among its most profound and impactful innovations was the electronic computer. Before its advent, computers were primarily people. These individuals, often women, performed complex calculations by hand. This human-powered computation was vital for scientific research, engineering, and government projects. However, it was a slow and laborious process prone to errors. The need for faster and more efficient calculations became increasingly apparent in the early 1900s. This need was further amplified by World War II, which demanded rapid advancements in code-breaking and ballistics calculations. It was against this backdrop that the first generation of electronic computers emerged. These early machines were colossal in size and limited in capability compared to today's standards. They relied on vacuum tubes, a relatively new technology at the time, for their basic operations. Despite their limitations, these pioneering computers laid the foundation for the digital revolution that would follow. They marked the dawn of a new era, one where machines would augment and eventually surpass human capabilities in the realm of computation. The first generation of computers, spanning from the 1940s to the mid-1950s, represented a pivotal moment in technological history. This era marked the dawn of electronic computing, a revolutionary shift from the mechanical methods that had dominated before. This era was defined by the use of vacuum tubes, a technology that enabled electronic switching and amplification. These devices were the heart of early computers, making it possible to process information at speeds that were previously unimaginable. These glass tubes, often resembling light bulbs, were essential components of the first computers. They were used in large numbers, with some early machines containing thousands of vacuum tubes. They controlled the flow of electricity, allowing these machines to perform calculations at speeds previously unimaginable. The ability to switch electrical currents on and off rapidly was a game-changer for computing. Vacuum tubes were a significant leap forward from earlier mechanical computing devices. These mechanical devices, which relied on physical components like gears and levers, were slow and cumbersome. These earlier devices relied on gears, levers, and other physical components to perform calculations. The mechanical approach was not only slow, but also prone to frequent breakdowns and wear and tear. This mechanical approach was inherently slow and prone to wear and tear. The constant friction and movement of parts meant that these machines required regular maintenance and were not very reliable. Vacuum tubes, on the other hand, offered a faster and more reliable alternative. They could handle more complex calculations and were less prone to the mechanical failures that plagued earlier devices. They could switch between on and off states thousands of times per second, enabling the execution of complex calculations at unprecedented speeds. This rapid switching capability was crucial for the advancement of computing technology. The use of vacuum tubes marked a turning point in the history of computing. It signaled the transition from slow and cumbersome mechanical computation to the lightning-fast world of electronics, paving the way for future innovations. It signaled the transition from slow and cumbersome mechanical computation to the lightning-fast world of electronics. This shift was monumental, as it allowed for the development of more sophisticated and powerful computing systems. However, vacuum tubes were not without their drawbacks. Despite their advantages, they had significant limitations that would eventually lead to their replacement. They were bulky, generated significant heat, and were notoriously unreliable. The heat generated by vacuum tubes often required elaborate cooling systems, and their size made early computers extremely large and cumbersome. These limitations would eventually lead to their replacement by transistors in the second generation of computers. Transistors were smaller, more efficient, and far more reliable, marking the next major leap in computing technology. First-generation computers, for all their computational power, were limited by the input and output methods available at the time. These machines, which were the size of entire rooms, were marvels of engineering but had significant limitations. Punched cards, thin cardboard sheets with strategically punched holes, served as the primary means of feeding data and instructions into these early machines. Each card could hold a limited amount of information, and the process of creating and managing these cards was both meticulous and time-consuming. Each hole pattern on a punched card represented a specific character or command. The arrangement of these holes was crucial, as even a single misplaced punch could result in errors that would take hours to diagnose and correct. Operators would painstakingly create these punched card programs, often requiring thousands of cards for even relatively simple tasks. The sheer volume of cards needed meant that entire rooms were dedicated to storing and organizing them. Once the cards were prepared, they were fed into a card reader, which converted the hole patterns into electrical signals the computer could understand. This process was not only slow, but also prone to mechanical failures, adding another layer of complexity to early computing. The output, typically numerical data, was often printed on more punched cards or paper using connected output devices. This meant that the entire cycle of input, processing, and output was heavily reliant on these physical cards. This reliance on punched cards made programming and using these early computers a laborious and time-consuming process. The physical nature of the cards meant that any changes or updates to a program required creating new cards and refeeding them into the system. Adding to the challenges of using first-generation computers was their limited memory capacity. These machines had very little memory by today's standards, often measured in kilobytes. These early machines had only a fraction of the memory available in even the most basic smartphones today. This limited memory meant that programs had to be extremely efficient and concise, leaving no room for unnecessary code. This limited memory constrained the complexity of the programs they could execute and the amount of data they could process at any given time. Programmers had to be highly skilled in optimizing their code to make the most of the available memory. Programmers had to devise ingenious ways to work within these constraints, breaking down problems into smaller, more manageable chunks that could fit within the available memory. This often involved creative problem-solving and a deep understanding of both the hardware and the software they were working with. In the annals of computing history, few machines loom as large as the Electronic Numerical Integrator and Computer, or ENIAC. This groundbreaking invention marked a pivotal moment in the evolution of technology. Completed in 1945, ENIAC was the world's first general-purpose electronic digital computer. It was a monumental achievement that set the stage for future advancements in computing. Housed at the University of Pennsylvania, this behemoth occupied a massive room, spanning 1,800 square feet. The sheer scale of the machine was a testament to the ambition and ingenuity of its creators. Its sheer size reflected the technological challenges of the era. The complexity of its design was matched only by the dedication of the engineers who built it. ENIAC was a marvel of engineering, boasting over 17,000 vacuum tubes, 70,000 resistors, and 10,000 capacitors. Each component played a crucial role in its operation. It consumed a staggering 150 kilowatts of power, enough to illuminate a small town. This immense power requirement was a reflection of the machine's groundbreaking capabilities. Despite its size and power consumption, ENIAC was a significant leap forward in computing power. It represented a new era where electronic computation became a reality. It could perform 5,000 additions per second, a remarkable feat at the time. This speed was unprecedented and showcased the potential of electronic computers. Originally commissioned by the US Army for calculating artillery firing tables, ENIAC's capabilities extended far beyond its initial purpose. It quickly became a versatile tool for various scientific and military applications. It played a crucial role in the development of the hydrogen bomb, weather prediction models, and other scientific breakthroughs. ENIAC's versatility and power made it an invaluable asset in numerous fields. Though eventually superseded by more advanced machines, ENIAC's impact on the trajectory of computing was profound. It laid the groundwork for the development of modern computers and inspired future generations of engineers and scientists. It demonstrated the feasibility of large-scale electronic computation and ushered in the era of digital computing. ENIAC's legacy lives on as a symbol of innovation and progress in the world of technology.